Many quantities we care about in political science are latent: ideology, knowledge, democracy, sentiment, and many others. We do not observe X directly. Instead, we estimate it from indicators. So the first object we get is a noisy estimate. Tilde X equals X plus U. But latent variables also require identification. In practice, we usually put both the true latent trait and the estimated score on a mean zero unit variance scale. That second step matters. The estimate is noisy, but after standardization, it has the same variance as the target latent trait. Here's the intuition. The top row is the true latent variable, X, identified to have variance 1. When measurement error is added, the noisy estimate tilde X spreads out. Its standard deviation is the square root of 1 plus sigma u squared. But the score we use in the regression is not usually left on that wider scale. We standardize it, producing X hat. So as the noise grows, the middle row gets wider, but the bottom row is compressed back to the identified latent scale. This is why the latent predictor case is not the same as ordinary classical measurement error. In the ordinary classical error case, the observed predictor has inflated variance, so the slope is multiplied by 1 over 1 plus sigma u squared. For an identified latent predictor, the variance inflation has already been removed by standardization. That changes the slope multiplier to 1 over the square root of 1 plus sigma u squared. The two curves are not the same. The latent predictor slope is still attenuated, but it is attenuated by the square root factor because the scale has been reset. The correction uses the fact that the same latent trait can often be estimated from two disjoint sets of indicators. Each split gives a noisy measurement of X. If the split-specific errors are independent, then the correlation between the two identified scores estimates reliability. Rho equals 1 over 1 plus sigma u squared. In the latent predictor case, the unadjusted regression slope converges to the square root of rho times the true latent scale slope. So the correction is simple. Divide the unadjusted slope by the square root of rho. Visually, the blue bar shows attenuation. The corrected green bar restores the slope to the latent scale. The takeaway is that latent predictors combine two issues: measurement error and scale identification. Because the estimated latent score is standardized, standard errors in variables intuition does not carry over directly. But split indicators give a modular way to estimate reliability and correct attenuation. Compute rho as the correlation between the two split-based scores, then divide the unadjusted latent predictor slope by the square root of rho. Latent predictors are not just noisy variables. They are noisy variables on an identified scale. The correction has to respect both pieces,